So my name is Sébastien. I work for Alfamation for 10 years now, and I'm going to talk today about the functional testing of micro-optics, especially for PICs, datacom and telecom applications. So basically interconnection optics. Just a few words about me. I have a background in optics. I did my study in France, where I studied optics with an engineering degree. And since then, I worked in optical applications for vision tests and also micro-optics tests for functional testing. Just a few words about Alfamation. It's an Italian-based company. We are near Milan, in the north of Italy. We are part of the Intest Corporation since earlier this year, and we have now presence worldwide thanks to the other office of the corporation, which helps for the service worldwide to the customers. And Alfamation is strongly characterized by a very strong engineering team. Over the years, we developed a lot of innovative test solutions in different markets, like consumer electronics, automotive infotainments, including also micro-optics and photonics devices. The photonics testing in Alfamations already happened 15 years ago, where we did some active alignment system for assembly of fibers connectors with active alignment and gluing, curing, and so on. It's something that is in the past now. Today we are doing different application in optics. I'm going to talk about just after this. This is an overview of the systems that we do at Alfamation. So we do functional testings. The main business is for infotainment system, automotive central units, electronic testing. We do have also systems to test displays, so checking the uniformity, color, pixel defects, for automotive mainly, but not only. And we do have also a platform to test micro-optics on wafer, and this is the topic I'm going to discuss today. And on this platform, we developed in the past years several test applications to test micro-optics. I'm just going to give you an overview. One of them is to test micro-optics that goes into 3D sensing for consumer electronics, where we test the DOE or the meta optical element that goes to project dot patterns, light patterns on the hands or face for recognition, for example. And for this, we use a conoscope lens, and we inspect each single lens on the wafer, DOE on the wafer, and we can reach speeds up to 3,000 units per hour. Another application is similar because we are testing the lens which goes before the DOE. So it's a collimator lens, which has the function to collimate the light from the VCSEL. And to test it, we insert a divergent beam into the lens. The collimated beam is steered to a beam profiler, and then we analyze the minimum spot size, and we get information like focal length, efficiency, and here the speed is slightly slower because we need to do some focus scan, acquiring more images, but still we can measure 1,500 units per hour. Another application that we talked about a lot yesterday, I'm going quickly today because we want to talk more about telecom application, but we test also the MLAs that go into projecting light on automotive. Here the example is welcome carpet. We are looking also right now to propose a solution also for front light illumination. Still always on wafer level, reaching speeds up to 2,500 units per hour. And here we come in the topic which is more of interest of us today regarding coupling optics or interconnecting optics. This test application, we did it a few years ago. It was not for telecom, but we had to test an MLA which had the function to focus the light coming from the outside world on an array of photodiodes. The function was a spectrometer in the near infrared for a consumer device. which at the end I think never picked up for the consumer application. But we did test this MLA, and how we tested that is what we injected a collimated beam inside the MLA around 950 nanometers, and with microscope-like vision system we scan the spot size after the MLA, so we get the spot size at different position. We find the best focus, and this way we can measure the flange focal length, the best focus position then, and we can get the efficiency, flange focal length, uniformity of the different channels on the MLA. Here also reaching speed of about 1,500 units per hour. From this, our intention is to derive this kind of testing also for the interconnecting optics, because it's quite similar in the way it is working. Maybe the scale is different, but gaining from this, the idea is to tackle some new challenges. So I don't have today a solution to present to you, but the idea is for me to present to you what are the competencies that we developed in the years and what can be leveraged to test interconnecting optics. So we are looking today for opportunities to collaborate on new devices, to test them on wafers, but not only. I will show you later. So typically, when we talk about functional testing of micro-optics, we often are compared to morphological testing. So comparing the shape of the micro-optics, so measuring the radius of curvature, the thickness, the diameter, and so on, and in comparison with the functional testing, where we want to see the coupling efficiency, for example, the focal length, both present pros and cons in the method. For morphological, the main advantage is that standard equipment exists and you can apply it on a very wide range of micro-optics without retooling and so on. The cons is that maybe you are overkilling because your parameters are not directly linked to the application. So maybe you are rejecting lenses which will still have a function which is acceptable for the application. So when you come to a functional testing, you kind of have the opposite pro and cons, that functional testing needs to adapt to each single device in terms of wavelength, output, inputs, channels layouts, whether it is single, linear layout, matrix layout, the lens diameter, the pitch, and so on, because we need, of course, to inject light, to collect the light, different wavelengths, and so on. So the tester needs to be very flexible. Here I just put some schematics of the kind of setups these devices can be used for. The MLA is one of the examples to focus on the photo detector array. It can be also a PIC devices. And also we talked recently with the potential customers. Also today again I discussed with the testing waveguides array that will be used in interconnecting inside PICs devices, and this is the kind of opportunities we are looking at. And to work on this at the end, at Alfamation what we do is we make automated test equipment, and we try to make them good test equipments. And to do this, we always aim to have high throughput by using parallel processes, batch sequences, and optimize the test sequence as much as possible, while we keep always in mind to have a reliable testing. So we always aim to have good gauge R&R performance in terms of stability, repeatability, and also we always, even maintaining the good test results, we always aim to optimize the cost by maybe integrating hardware which is not too much expensive, and optimizing also the test time and the test scope to focus on the parameters that are relevant for the production and the mass production. Here are some examples of flexibility that we have to adapt to different scenarios. For example, testing different shapes of wafer. We also have capability in-house to design beam shapers, to have different parameters like different polarization, divergence, intensity profile, shapes and size of active area. We are also very good at positioning. This is an example of stepping from one device to the next one on wafer. These are two examples of stepping, 2 mm step and 10 mm step, and we can be within 3000 nanometer position on the next device in a few hundreds of milliseconds. And yeah, this is an example of batch testing. It is a strategy that we use when we have on the DOT several tests to perform. It can be a flange measurement, a focus measurement, and then, for example, spectrometer measurement. It depends on the application. But if between each measurement we need to reconfigure the tester in some way, we might lose time on each devices to do the reconfiguration. So what we do is we test the devices in batches for test number 1, and we go back and we do test number 2 on the same set of devices, test number 3, and this way, in some cases, we can reduce the test time and maintaining the same test scope. So this is it. This is to give you an overview of what we do. The important thing to remember is that we are looking for opportunities to develop new test applications, whether you have test methods that are already tested in laboratory and you are looking to integrate them in an automated system. We do have engineering capabilities to do it in an efficient way. We are looking for micro-optics photonics devices that needs to be tested, of course. And I talked about wafer level testing, but here I just give an example of 2 other platforms. This one is a pick and place platform where you can test single device after dicing, or also modules which are already integrated with all the electronics or maybe the light source integrated, and we can do electrical contacting, some alignments, and optical analysis. And this is a platform which is manual loading, where we can put here in the test socket, we can load the module, close it manually, and then test sequence can go automatically done. So I would say visit us at our booth, but it's almost the end of the event, but we already meet a lot of you already. So we are located in Italy. Do not hesitate to contact us if you have any interest in collaborating on this testing. You do have my information here to contact me directly.